Welcome to our presentation on self-supervised learning for place representation generalization across appearance changes. My name is Mohamed Adel, and I am excited to share our innovative research with you, conducted at SNT University of Luxembourg. This study explores a novel approach to visual place recognition, key to unlocking spatial navigation for animals, humans, and robots. Visual place recognition, crucial for applications like autonomous driving and augmented reality, involves matching images to a database despite varying conditions like weather or obstructions. Achieving invariance to environmental conditions and viewpoint changes while distinguishing different places is challenging. Traditional methods, often supervised, struggle with unusual conditions. Our work uses self-supervised learning to create robust place representations against appearance changes and sensitivity to geometric transformations. This approach combines contrastive and predictive learning, termed CLOSPNet. CLOSPNet stands for Contrastive Learning with Appearance Augmentations and Spatial Prediction. Learns discriminative place representations that generalize to new conditions. It overcomes the limitations of supervised learning, which often requires extensive data annotation, by using self-supervised learning and combining appearance and geometric transformations. CLOSPNet's goal is to force the model to learn features invariant to drastic appearance changes, effective for visual place recognition. The training of CLOSPNet involves creating augmented versions of original images, pivotal aspect of CLOSPNet, to enhance model robustness and adaptability. Our model employs a range of pixel-level data augmentations for triggering appearance invariance bias. These augmentations include variations in lighting, contrast, and color adjustments, among others, carefully chosen to improve performance based on empirical evidence. Moreover, geometric augmentations are also a key component. We incorporate information about rotations in the image representation, focusing on a cyclic group of 90 degrees rotations. In CLOSPNet, we employ a combination of contrastive and predictive losses. The contrastive loss is applied to bring closer the representations of the same place under different conditions while ensuring that representations of different places remain distinct. The predictive loss involves classifying images based on their rotation angles. Our overall loss formula combines these two aspects to enhance the model's robustness to appearance changes and its sensitivity to geometric variations. In the inference stage of CLOSPNet, the model's practical applicability is demonstrated. After training, we employ the appearance invariant module to process a set of reference images. This involves passing these images through the model's encoder and mapping them to a latent representation space for L2 normalization, thereby building a reference descriptor bank. During inference, when a new query image is introduced, CLOSPNet efficiently compares its representation against this descriptor bank. Utilizing a k-nearest neighbor approach, the model then retrieves and identifies the most similar images from the reference set. This stage is crucial as it showcases CLOSPNet's ability to effectively recognize places under varied environmental conditions, a key requirement for robust visual place recognition. Our evaluation shows that CLOSPNet significantly outperforms standard baselines on datasets that have a dramatic appearance change. This performance, achieved with a simpler architectural foundation compared to more complex methods, underscores the effectiveness of CLOSPNet in handling diverse and challenging visual place recognition scenarios. We can see examples of queries and best retrieved images, along with GradCam activations. These visualizations demonstrate that CLOSPNet, even if trained without any labels, was able to learn features meaningful for outdoor localization tasks, such as skylines, for instance. In conclusion, our paper presents CLOSPNet, a model leveraging self-supervised learning for robust visual place recognition. The model's ability to learn from unlabeled data, adapt to various environmental conditions, and recognize geometric details highlights its potential in real-world applications. Our findings open pathways for further research in visual place recognition, particularly in addressing viewpoint variations and exploring more complex architectural elements. We thank you for your attention.